Reactions involving the collision of just one or two particles or reactants occur very frequently. Whereas if we were to include three or more particles in our reaction, it's actually quite rare, only because you have to achieve the right amount of energy when colliding the reactants together, but also the correct orientation. So, scientists believe that most of these chemical reactions actually occur in steps, in a particular sequence. When you put these steps together, this is known as the reaction mechanism. Adding the mechanism, all of these steps together, you get the overall reaction. We can illustrate our reaction and therefore the stepwise reaction in our potential energy diagram. Now, typically, we always see in our potential energy diagram as we proceed through time, we start off with reactants and then we have a regular profile to our products with a single activation energy. So, this is what I wanted to draw something like this. But if we break it down into its steps, each step should include an activation energy as well as an activated complex with at the transition state. Um, if we look at the reaction mechanism based on the overall reaction, step one always includes the actual reactants. The final step three in this case, will always have the final products from your overall reaction. When we bring it over to the actual diagram, the reactant to the first intermediate here, our products here, is our step one. So from here to here will be step one. We have an activated complex, which recall it is the structure with high energy that kind of looks like a hybrid between the reactant and, in this case, the intermediate. It's quite unstable and it always is at the transition state, transitioning from one stage of the reaction to another. If you notice, you have two intermediates for this reaction. An intermediate are structures as well, just like our activated complexes, but they're more stable, hence their lower energy levels. We can actually isolate them during the reaction progress from the reactant to the final product. They always appear in your reaction mechanism as products, but they never show up in the overall reaction because they form, but they also get consumed. To complete the picture here, we can notice from the intermediate here, we can set that for step two as a reactant, and we get a secondary product over here, which is your intermediate step. So this would be step two with its own activation energy and its own activated complex at the transition state. Step three includes the final product. So we're going from the intermediate. This is your product here. We're going to replace it as our reactant for our final step, and then our final product that we actually observe. So this becomes step three. We're not limited to three steps in a multi step reaction. We could have two or even four steps, for example. As mentioned before, the intermediates appear in the elementary steps, but not in the overall reaction because they form and consume within the mechanism, meaning they get crossed out. So if we look, for example, our N2O2, we can see this get crossed out because it appears on the product, but in step two, it appears as a reactant. Same with the hydrogens here. We can cross those out. We also have N2O crossout because they appear in both the reactant side and the product side. And also for our H2 here, we have 2H2, 3H2, but we only have one H2 here. These can get crossed out. And finally, you can also cross out your waters here and here as well. What you're left with, once you add them all together, you should have your final or overall reaction where you have 2NO, 2H2 are as your reactants, but also N2 and 2H2O as your products. The reaction intermediates are the compounds that you crossed out. So we have H2, we have N2O2, as well as H2O and N2O. Now, I know that water and hydrogen, we cross, it still appears on the overall reaction, but because we also cross them out, it would still be considered a reaction intermediate. When a reaction takes place in a series of steps, the overall rate of the chemical reaction is determined by the rate of the slowest step. And this slowest step is also known as the rate determining step. So instead of calling it rate determining step or the slowest step, we just use RDS to represent that. So once we know the overall reaction and the stepwise reaction, we determine which one is the slowest one. From that step, we're going to determine the rate law equation. The rate in general, let's come up with a general reaction. Let's do A plus B makes products. For the rate law equation, we only care for the reactants, so A and B for this particular example. We still need to balance our overall reaction. So instead of putting a coefficient of an actual numerical value like 1 or 2 or 3, in general, we'll just put X and Y to represent that balanced chemical equation. And these are our coefficients. The rate law is going to be based on the rate determining step, so your slowest step. So let's just say that this is the slowest step that we've identified. We're going to make the rate equal a K constant, which is known as the rate constant, multiplied by the concentration of your reactants. So concentration of A multiplied by the concentration of B. But we need to acknowledge those coefficients. Those coefficients become their respective exponents. So if you had a 2 for A, it would be A squared. So in general, we have A, the concentration of A to the exponent of X, whatever that coefficient is, and then Y as our exponent for our concentration of reactant B. K is known as the rate constant, which makes the two sides of the equation equal each other. This is kind of like a fudge value. The rate constant is a value and it's different for every reaction. You can't really memorize it. It's not like pi where it's a definite value of 3.14159, etc. The exponent values are indicative of the coefficients in the front of the equation. So here. And then the concentration A and B are the concentration only of the reactants. So if we look back at example 1 over here, let's try and determine the slowest step. And we have to look at the elementary steps, not the overall reaction. If we look at the diagram over here, we notice that each step has its own activation energy. This is the barrier that each step must go through in order to get from the reactant to the product side. If we look at try and illustrate the activation energy, it's always from the starting to the top because we are reading this going forward. We notice that the activation energies are not equivalent to each other. So this is activation energy for step 1. This would be this activation energy for step 2. And then over here would be the EA for step 3. EA2 looks like it is the largest in energy. It requires the most amount of energy to get from the reactant to the highest energy level, such that it will transition now to moving forward in the reaction to produce that product. So, since EA2 has the greatest energy barrier to overcome, this will be our rate determining step. This is going to be the slowest. Relative to EA2, this is going to be really fast just because it is a smaller activation energy barrier. So, this is going to be fast, but also this one. This is probably going to be the fastest, step 1, but relative to step 2, step 3 is fast. So since step 2 is the slowest, that will be our rate determining step. So rate determining step would be step number 2. And I'm just going to write number 2 over here. And let me write the rate of the actual reaction, which is N2O2 plus 2H2, which makes your products. When writing down the rate law equation for this particular example, we only need to acknowledge the RDS, the rate determining step. To write the rate equation, we're just going to write rate is equal to some constant K. And remember, it's different for every example and for every different reaction because they'll all have different rate determining steps. So it's some K value with the concentration of A. And in this case, we can use this as A, our first reactant. The exponent for A is the coefficient for N2O2. And because this is understood as 1, the exponent will therefore be 1. We don't have to necessarily write that 1. It's understood if we don't write anything here that that is 1. So N2O2 to the power of 1. And then our second reactant here is hydrogen, H2. It definitely has a coefficient, so it will have an exponent. It's H2 squared. So this is the rate law equation for example 1, and here is the rate determining step because it is the slowest step. It has to overcome the greatest activation energy barrier, and therefore it is the longest pathway.